In this video, we are going to look at the Euler's method of finding a numerical solution to a given differential equation. Assume that we have a differential equation dy by dx is equal to f of xy with a particular solution x naught y naught. So if x naught y naught is a particular solution, what does that mean? It means that we know x naught y naught is a point on the solution curve. So by solving this differential equation, it represents, every differential equation represents a family of curves. So when you solve this differential equation, basically when I integrate this f of xy, it will give me a curve, but it gives me, in fact, a family of curves. There's a plus c on it. Okay, and what this says, we haven't solved it. Okay, so that's the main thing. We haven't solved the differential equation, but we know that x naught y naught is a point. This is a point on the solution curve. So when the x value is x naught, the corresponding y value is y naught, we know, like 0, 2. So we know that 0, 2 here is a point on the solution curve. But you should remember that we don't know what this curve is. And the question is to find out if f of 0 is 1, f of 0, x naught, y naught, I'm taking it as 0, 1. F naught, x naught, y naught is 0, 1. So what it means is f of 0 is 1. Then maybe the question is like, if f of 0 is 1, find f of 10. F of 10 means when x is equal to 10, what's the corresponding y value? So when x is 0, the corresponding y value is 1. And when x is 10, what's the corresponding y value on the solution curve? So I need to move from x naught by 10 units the right side and find the corresponding y value on the solution curve. But unfortunately, we don't have the solution curve. So what I had to do is I need to move by 10 units the right side and then find the corresponding y value there. So what we are actually going to do here is we are trying to move to the right side. So we'll say, okay, so to start with, I'll say let x naught y naught be considered as xi minus 1 and yi minus 1 as a general situation. Instead of 0, 1, x naught, y naught, a particular value, I put it in a general format so that I could talk about any single point on the curve. So I'll say consider the point x naught, y naught as xi minus 1, yi minus 1. Be a known point, be the given point on the solution curve. What we are going to say is this x coordinate of the initial point, which is given to us. In fact, it was our x naught, y naught. We called it as xi minus 1, yi minus 1. We'll say let the x coordinate xi minus 1 be given a small increment h. Now, why do we say a small increment h? If I move 10 units to the right, okay, if I move 10 units to the right side, I will reach that point, the given point 10, for which I need to find out the corresponding y value. So I'm going to say that 10 is represented by h. Now, why did I say small increment? We come to that. Then the x coordinate of the new point will be xi minus 1 plus h, because it moves by h units to the right side. So that's a new x coordinate. Let the new point, when I do that, I have a new point on the right side because I am moving by h units to the right side, and the new x coordinate will be that plus h, x minus 1 plus h. I'm going to call it as xi because the second point corresponding to xi minus 1, the very next point. So it's xi, and let the corresponding y value be yi. So my approach here would be, I would somehow find out an expression or a method to find out this new yi without actually solving the differential equation. If I have the solution, just substitute xi into my solution curve and I get the corresponding y value. But this is without solving the differential equation, without knowing what the solution curve is. I need to find out what is the corresponding yi value. After I give a small increment of h to my xi minus 1, I have a new x value, but what is the corresponding y value? I want to find out an expression, a method to find that yi value without actually solving the given differential equation. This is going to be our approach. Okay. If h is very small, that is, this increment which I am giving to the right side is very small. The difference between the initial point xi minus 1 and the new point xi, if it is very small, you can see that the error which we could make be as minimum as possible, because it's very close to the initial point. So since it is very close to the point, the deviation of that new point from the original curve could be very minimal. Like when I move HU onto the right side, we don't know what's the corresponding. When I don't know this point is how far from the original curve. The deviation could be more. But if I am very close to the initial point, the deviation of my new point from the original solution curve could be very minimal. That's why we say if h is very small, we can approximate that this new point xi yi, which you see here far off, if it is very close to the initial point, it will be almost on the solution curve. That's why we say if h is very small, we can approximate this point to be on the solution curve. So I'm trying to get a point which is very close to the given point, but will still lie on the given curve, or approximately lie on the given solution curve, not the solution curve of the given differential equation. So since we have 2 points on the given curve, I can say the gradient of the line PQ, this line PQ, and since Q is very close on the curve, the gradient of the line PQ, which is y2 minus y1 by x2 minus x1, y difference over x difference, you can see yi minus 1 divided by xi minus 1 is equal to yi minus 1. The numerator remains the same, but the denominator, the difference between the two x coordinates is the increment, the step you have taken forward, h, the step value h. So this is the gradient of PQ. But since Q is almost on the curve, shouldn't this be approximately equal to the gradient of the curve, which is dy by dx at the given point? Do you get that idea? Since the step we have taken to the right side, the h value is very small, the point Q will be as close as possible to the given solution curve. So Q almost lies on the solution curve, and therefore slope of, or the gradient of PQ will be same as the gradient of the curve, which is dy by dx. But at which point? At the given point xi minus 1, yi minus 1. So I'm going to say this slope which I calculated for PQ is dy by dx at xi minus 1, yi minus 1. But dy by dx is equal to f of xy. That's what they told you, the differential equation. At xi minus 1, yi minus 1, when they say f of x comma y will become f of xi minus 1, yi minus 1. I cross multiply h to the other side, so it is h times f of x minus 1, yi minus 1. Then I move this minus yi minus 1 to the other side, it becomes plus there. So I get a formula for yi. Yi is the previous y value, which we know because xi minus 1, yi minus 1 is in fact my x0, y0 given to me. So this is actually my y0, just the previous value. So if I can find out the yi value using the previous y value plus h times the given point, the function value at the given point, f of xi minus 1, yi minus 1. So this is your dy by dx is equal to f of xy. Into that I replace x by xi minus 1 and y by yi minus 1. This is my dy by dx, the gradient at xi minus 1, yi minus 1. This is not the solution curve. F of x comma y is your dy by dx, which means it's the derivative at xi minus 1, yi minus 1. That's the meaning, this one. So using the derivative dy by dx value at the given point, times it by the step value, add the given y value to it, I'll get the next y value. Think about it. Let's say 0, they said f of 0 is f of 0 is 1. So 0 comma 1 is the initial point. Using that, I can find out a point which is very, very close to it, like 0.1. I can't find out f of 10 because 10, since it is very far, may not be close to the curve. But if I do f of 0.1 or probably f of 0.00001, very, very close to it, using this formula, I'll be able to find out the corresponding y value, which will be on the curve. Then I take these small steps. Every time I'll add 0.00001. Again, I add 0.0001. So I'll take very, very small steps like that to finally reach f of 10. And I get the corresponding f of 10 value. So that's basically the idea. Okay, so this is actually a particular solution at the new point xi, when the initial value xi minus 1, yi minus 1 is given. So this is basically the idea. So we can find out the particular solution to the given differential equation at any given point xi, like the 10 I was talking about, when the initial value 0 comma 1 is given, like that. I'll take small steps to the right side until reach maybe point, if I say 1 unit step, if I take from 0 I'll go to 1, from 1 I'll go to 2, like that I'll reach finally 10 and I get f of 10. Okay, that's the meaning. Okay, so here h is the increment or the step value. So smaller the h value, we make the more accurate the numerical solution going to be. I have a question here, dy by dx is equal to e raised to x plus 1 with an initial condition 0 comma 1, and the question is to find out the value of the function at x is equal to 0.5. So dy by dx is e raised to x plus 1, f of 0 or y of 0 is equal to 1, which means when x is 0, y is 1. Estimate y of 0.1. Find the value of the solution when x is equal to 0.5. And this is my f of xy. Or rather, here it's only f of x. There is no y in it. There could be y in it as well. So dy by dx is equal to e raised to x plus 1. They suggested, this is called the Euler's method. They suggested that h is 0.1, which means if I take 5 steps, I'll reach that point on the right side. 0.5. From 0, I need to reach 0.5. From y of 0, I need to reach y of 0.5. So 5 steps I'll take with 0.1's size. So since the step size is very small, every time I move to the right side, I'll be as close as to the original curve. That's the idea. So I'm writing the formula which we derived. Your new yi will always be yi minus 1 plus h times, h is 0.1, times f of x minus 1, y of I minus, f of x I minus 1, y I minus 1. So what is my f of xy? F of xy is dy by dx is equal to f of xy. This is my f of xy. But notice that there is no y in it. So I could say dy by dx is equal to f of x. So into my f of x, I should replace x by I minus 1. So this is going to be e raised to x I minus 1 plus 1. E raised to x I minus 1 plus 1. Okay, so that's the relation for finding yi. I'm trying to find out yi. Okay, so that's how I find this is actually f of x. Yeah, so that's where we reach. Okay, and now I copy that differential equation again. Dy by dx is e raised to x plus 1. Y of 0 is 1 is the given condition. Estimate y of 0.5. I make a table. This is my initial value, xi minus 1. This is the corresponding y value. So this is the initial point, xi minus 1 and yi minus 1, using which I will find out the very next point, which is xi yi. So xi minus 1, yi minus 1 is given to me, using which I'll find out xi yi, the new point, a point which is very close to it on its right side. So the given point is 0, 1. When x is 0, y is 1. We know f of 0 is 1 means when x is 0, y is 1. So the new point xi will be, you are taking a step value of 0.1. So the new x value will be from 0, it increases by 0.1. So xi value is easy from xi minus 1. Just add h to it. 0 plus 1 is 0.1. But y value is not that easy. That's why we have this formula yi is equal to yi minus 1. Yi minus 1. Yi minus 1. What is yi minus 1? The initial y value, which is 1, plus h into. This is h into 0.1 into f of x I minus 1, which is e raised to xi minus 1. The original x value, e raised to 0 plus 1, which when I put into a calculator, calculate it, I get 1.2. And now, so the new set of point becomes, the new point on the right side is 0.1, 1.2. Do you get that? So I'm going to repeat this process with this as the known point on the curve, because this is as close as possible to the curve. So we approximate that 1, 1.2 is a point on the curve. So that's my new point. 0.1, not 1, I'm sorry, I said 1. It's 0.1 and 1.2. So 0.1, 1.2 is a point which is very, very close to the given original point on the curve. So using this, I'll find out its very next point, which is a 0.1 step away from it. So I'm going to find out the new x and y using the new point which we have here. So 0.1, I take 0.1 step to the right side, h value is 0.1. So this 0.1 will become 0.2. And then to find out yi, I use the same formula using 0.1 and 1.2 as the new values here. So let's see how it happens. So 0.1 became 0.2. Now into this formula, yi minus 1 and xi minus 1 will be 1.2 and 0.1. You see here, yi minus 1, 1.2, the new y value, plus 0.1 into the h value into e raised to xi minus 1. Xi minus 1 is 0.1 plus that one there. Put into the calculator, I get. So now I know that 0.2 and 1.4105 is the very next point, which is as close as possible to the curve, or rather it actually lies on the curve, we say. So 0.2, 1.4105 is known to be on the curve. Using that, I can find out the next point. So I take this as my initial point. This 0.2 and 1.4105 is my new point. Using that, I'm going to find out the very next point by going h step to the right side. The step value is h to the right side. H is 0.1. So 0.2 will now become 0.3. And what is the new y value going to be? This formula, where yi minus 1 and xi minus 1 will be the new set of points. So yi minus 1 will be 1.4105 plus 0.1 into e raised to xi minus 1. What is xi minus 1? Xi minus 1 is 0.2. So e raised to 0.2 plus 1. See, that's what I have written here, which works out to be this number. So which means 0.3, 1.6327 is actually a new point on this curve. So that's the new point which is known to be on the curve. Use these points to find out the new x1 and y1, which is the very next point to it. The point which is very close to this, so that it will continue to be on the curve. So this is my initial point, new xi minus 1, yi minus 1. I will use that to find out the new xi and yi, the very next point. For that, I should take 0.1 step to the right side. So 0.3 will become 0.4. And then to find out yi, I put yi minus 1 as 1.6327 and xi minus 1 as 0.3 into this formula. So that's going to be 0.4, and then sub in that, calculate it, and I have the new point 1.8676. So the new set of point is 0.4 comma 1.8676. So that's going to be the new point for me. Use that point to give 0.1 step size movement to the right side, which will give me the required point. So that is 0.1 size to the right side, step size. 0.4 will become 0.5, and use 0.4 as xi minus 1 and 1.8676 as yi minus 1 to get my new yi. Yi will be yi minus 1, which is 1.8676 plus 0.1 into e raised to xi minus 1 is e raised to 0.4 plus 1, which is what I have written, and that's the answer. So which means when my xi value is 0.5, the corresponding yi value is 2.1168. What does that mean? When x is 0.5, the corresponding y value on the solution curve is 2.1168, which means f of 0.5 is equal to 2.1168. Now we did this without actually solving the differential equation. We did not solve this differential equation. We used the Euler's method to get the numerical solution to it at x is equal to 0.5. Now, that's the Euler's method, guys, but just to convince you, suppose we did it the usual way. This is the differential equation. Y of 0 is 1. Estimate or calculate. I should have written probably calculate. It's calculate y of 0.5. Evaluate. I should have said that way. This estimate, I took it from the previous question. Approximating it was. So to find out y, I should integrate it. When I integrate it, I'll get e raised to x is e raised to x itself. 1 becomes x plus c. And the initial condition is y of 0 is equal to 1, which means when x is 0, y is 1. When I do that, I replace y by 1 and x by 0. So I'll get c is equal to 0. Therefore, my solution y is equal to e raised to x plus x. And so I have the solution curve now, e raised to x plus x. And my question is to find out y of 0.0. So now what is y of 0.0? Replace x by 0.0. I said, what did I say? Y of 0.5 is what I need. So what is y of 0.5? Y of 0.5 will be e raised to 0.5 plus 0.5, which when I evaluate, I get 2.1487 against 2.11 something which we got earlier. So this is pretty close. I mean, this is the actual value, of course, approximated because of E. And the Euler's method gave me a value very, very close to it, 2.11 something it gave me. And if I, instead of 0.1, the step size, if I had made it 0.0001 and taken so many steps to reach 0.5, my answer would have been as close as possible to this. That's Euler's method, guys. Yeah.